So, welcome everyone. As you're probably all aware by this point, this is a 4-day training that Tomas and I have put together to walk people through really the building blocks of automation APIs with Arista products, and then jumping into Ansible and finally ending up with AVD, which for those of you who don't know, AVD is currently our big out-of-the-box, quote unquote, just work solution for customers that want to use Ansible and optionally CDP to manage their entire network fabric. So the schedule for this is going to be fairly packed. Day one today, we're going through some background on automation and different concepts of how we approach this and how you advise customers to start their automation journey with networking. We're then going to get into a variety of kinds of APIs and do some exploration with those. Specifically, we've been covering both JSON RPC APIs and REST APIs. We'll go through a quick primer of some basic Git operations, and then we're going to make sure everyone can access their AT topologies and run through the labs. For today, we have about 4 labs. Tomorrow's going to be 3 labs, and for day 3, that is going to be 1 lab. All the days are set up to be roughly half slides, half lab time. So we'll take the opportunity to work through looking at the slides. Going into day 2, we're going to start taking what we built on day 1 with APIs and Arista product integration to start talking about how Ansible improves upon what we could accomplish ourselves in just basic Python scripting. We're going to go through both the EOS and CVP Ansible collections we have and what those allow you to accomplish easily. And then, like I mentioned, we'll have some labs on those. Jumping to day 3, we're going to take what we've then discussed from day 1 and 2 for APIs and Ansible and show you how that all ties together to make the AVD monolith. We're going to look at how the stacking layers and playbooks we have there allows us to create this end-to-end orchestration for customer network. And then we have a lab put together where you will actually deploy an AVD fabric within your AT topology. And you'll go through some different exercises around modifying that, looking at how we do certain operations like IP addressing, things like that. Day 4 is currently for overflow. In timing, we've looked to be about on track, but in case we have more questions than expected or labs are taking people longer than that, day 4 will allow us to then still address any other questions people have. So with that, let's talk about just today. Specifically today, we are talking about, like I mentioned, APIs, REST APIs, JSON RPC APIs. We're also talking about YAML and Jinja, which are respectively our main data storage format and our data templating format when we talk about both normal Python and Ansible use cases. So why do customers care about automation so much? There's a variety of reasons why customers look to do this. A big one for a lot of them is simply put cost reduction. We have a number of customers who measure network downtime, not just in terms of engineer man hours, but also in dollars lost. That could be our high frequency customers who must have network up during market hours, and after hours, they have very small windows. That could be our cloud scale providers where syncing outages could cost them a lot of money and they quite simply do not have enough people to do it manually. It could be regulated industries like hospitals where excessive downtime could lead to fines for them. There's also considerations we made for our customers around productivity and availability. When they bring in automation to their networking workflows, they can make their existing NOC and architect personnel more effective, and they can also reduce how long they're actually having to spend to make changes to a network. So for a lot of CIOs and CTOs, that's a very big incentive to start driving their networks towards this state. And then a big benefit for us has been that we've embraced as a vendor, and we provide very good hooks into our products to allow customers to do this. And so we're seeing a number of customers, especially in EMEA, really start driving towards this automation vision. Finally, automation allows us to both improve the reliability and performance of our network. We can use post-change scripts via systems like Batfish, manual Python checks, CPP, Ansible, to validate that after we performed a change, the network is in the state we expect, and it can perform the operations we expect. That could be things like verifying that you have your configs in place. That could be doing end-to-end ping testing. That could be verifying route tables. There's a number of ways we can look at doing that. Even with more advanced automation, we can go beyond route reliability and get to optimization. We might have customers that do things like pull routing tables from across the network and analyze those in a centralized place to determine better route summarization, things like that. One of the things you'll often see when customers start with automation is, you probably have some calls with customers already, we just don't have time. You'll have an engineer call in, we can tell them, we have a script for this, we have an automated way to do that, and they go, yeah, we've been busy, we don't have time, we're new to this. And that can be a significant roadblock when we are both getting started internally and working with customers on this. We really have to get past this to get those benefits talked on the previous slide. For a lot of customers and even internally, the discussion really ends up being, we have to slow down now and invest in these tools to get us to a state where we can then get the benefits and get the ROI from actually implementing these. Along with that, that informs what we look at automating. It's often simpler when we're looking at automating a network or automating a solution to start with discrete components and then build those up into larger automations. So common things you'll see people start with when they're looking at doing automation is they'll do basic information retrieval, pull the MAC table, pull the ARC table for your switches, do health checks with that, give me a yes, no answer on my console. Like we mentioned, it could do end-to-end ping testing. And these are all things that are on their own fairly simple to automate. And then as a user or as a company progresses, they can start gluing these pieces together to create more sophisticated and robust automations. We can also completely automate and generate and automate the pushing configs devices. We're going to go in this course through a variety of ways to do that, ranging from pure Python and then Cloud Vision with Ansible and all the way up to AVD. But at this point, there's a number of options customers can use to do this. And based on how far along their automation journey they are and their sophistication, we can find a solution that works for them. Like we talked about, when different orgs start going to automation, there is some changes that we usually see that they'll struggle with or they have to get into. One of the first big ones is that if a team is not used to having shared processes and workflows, something like a CI/CD pipeline in GitLab, even shared repos, things like that, when they first start out, it can be more brittle. You might encounter scenarios where an engineer at customer is like, oh, we can't run that currently. The guy whose laptop that script is on vacation. I don't have that data. It's in a spreadsheet somewhere, things like that. So usually what you'll see, especially when an account team is first engaging with a customer to start doing this, they try to start very small and then build them up to a more robust and continuous culture. So it might start with something as simple as, let's get your IP address data out of spreadsheets into an IP address management tool. And when we have that done, we can use that to start driving scripts by APIs, things like that. And you'll eventually see these customers come along. On the other side of that, we do have very large and robust customers like Zoom and CN Rail, where we are now seeing them do these fully Dockerized, fully containerized builds, where they'll take the entire fabric topology and push out in that fashion. So again, more automation to the customers. This also applies a lot when you start looking at how you can use automation internally, for example, in your own designs or your own library pros. It's best to start by what you spend a lot of time repeating or things that don't really require a lot of nuance. Target those, build automations, work from there. And as you build those building blocks, that then gives you more you can compose with to create solutions for a given problem. In addition to that, and something we do both publicly and privately with our repositories and our code base with our customers and our internal stakeholders, is we look at how can we, one, collaborate, and two, prevent reuse or prevent reimplementation. When possible, if someone's already done it or has a repo for it, it saves time to reuse that. If it's fit for purpose, reusing that code can save a lot of time and a lot of testing. It's already tried that ground before. So internally, we do this for a number of products, especially when we look at testing suites. You'll see that we have a number of common frameworks that are used to make those faster to write and use. And then for our customers as well, we have multiple organizations on GitHub where we will share code with customers. We have EOS Plus repositories. We have the CVP repositories, and we have SE written extensions as well in GitHub repositories for customers. So jumping away from our philosophy of automation, we're going to get more into now what an automation workflow for a fabric can look like, both with and without CVP. And then from there, we're going to get into looking at what tools and integrations and products you might use at each stage of that. When we start talking about doing a completely automated workflow for a given network fabric, you'll usually see something like this proposed. And what this is looking at here is effectively your workflow for how you're going to go from both user input and data sources like either spreadsheets, if they're very primitive in the journey, or data stores like an IPAM or general purpose database, into actually emitting the configs that are then pushed for devices on our fabric. So in any given environment, you're going to start with your raw data. Like we said, could be spreadsheets, could be a database, could be IPAM. That's usually joined with user input of some sort. You might have prompts for IP address schemes. You might have a user-fed file to select only a portion of the fabric to change. You could have naming conventions, things of that sort. These get aggregated by your workflow pipelines into your source of truth for your build. And that is your merged data set of what you plan to use to then drive your actual changes. That gets fused in your orchestration engine with other logic you might have in place, rules for your fabric, like this is L3 LS deployment, I must have this many links, things of that sort, along with a templating engine, which is where we'll get into tools like Jinja to actually take my data and my intent and then transform it into something that I can actually build and push out to devices. From there, you get into both change control and provisioning engines. This can be different things for different customers. Some customers have very formal change control processes where they might have to put automation and edits through a CAB, a change advisory board, or something like that. You can also have very informal customers who effectively just want to coordinate that the change happens after business hours and it doesn't affect the internet router. Both your intent and change control and your actual design and orchestration engine get pushed out via your provisioning engine, and you end up with a network fabric. So we're going to skip through some of these slides here, as I talked about already, just because they're mainly for those who have to watch after the fact. What I do want to talk about as well is that when we get to the source of truth, we really start talking about how we make sure we have both clean and structured data. That's important when we start talking about downstream operations with Python or Ansible, because if our data is not structured well, it's hard for us to work on. And if it's not clean, we can't trust that our changes will have the effect that we want. So this can be in various ways, but typically, when you're looking at the source of truth step in workflow, you're going to see a customer has either manual validation or some sort of automated way to make sure that their data matches the intent they want, both against their databases and what they're planning to do. In addition to that, you can validate data structures in a number of ways as well. We'll get into a few of those. And downstream tools might err out if you want the correct validation or the correct structure for your data. So this can be important. Fabric logic is something we're going to get into a lot when we start talking about AVD. We do enforce a lot of logic at that layer. For homegrown customer automation or simpler automations, this could be something like functions you've written in Python that just validate your addressing scheme and verify you haven't reused addresses for interfaces, verify that you don't reuse ASNs, things of that sort. But the goal of this is to give you that abstraction from having to do everything manually and explicitly, while also allowing you to reason about the patterns you're going to emit. Like we talked about, templating is usually going to be Jinja, and it's going to take your JSON or YAML, and it's going to create it into text that the switch connection understands. We'll get more into that later in this presentation when we talk about Jinja directly. And your orchestration engine is then what's doing most of the work. Depending on your solution, this can be a number of things. We'll show you a few examples of that. And then same for provisioning. So let's give you an example of what this might look like here with what tools we're using now. Let's take an example where I have a network fabric that I want to automate. I have Cloud Vision available to me. I might start with using Netbox, a database, or the Cloud Builder IPAM, which was an EOS Plus app for a number of years and is now becoming mainline in newer code. I could use Git, I could use YAML. I can feed all of this data in through my validation to my Python config builders or Ansible or just template building that I can use. Within Ansible itself, I have my Fabric rules, which we'll go into with some of our later labs. And I compose this data with Jinja down to my actual configs I want to apply. And I perform my operations against Cloud Vision. So once all my templating is done, Ansible fires off a number of REST API calls to Cloud Vision. It tells it, hey, here's these configlets, add them to your storage. Hey, you have these configlets now, map them to these devices, take those changes you've made. I want to run those tasks. And we can do all of that. So when all of this is in place for a customer, changes become very simple. Let's say that I decide in my IPM solution, oh, I made a mistake in how I'm doing the out-of-band management IP addressing. The customer can go in and change the IPs for his devices. They can go in and change the entire subnet. And then we can re-trigger our downstream playbook to go pull data from those devices or pull data from those databases, recompute our templates, recompute configlets if needed, push them out to Cloud Vision, determine what change we have to make, create the task, then push the task. That becomes very, very helpful for customers. Now it's no longer even having to think about, okay, well, I've made this change. Have I touched on my devices yet? I've made this change. Did it work? With this end-to-end kind of workflow in place, it becomes very simple and repeatable to make changes. So not only does it save them money, it also makes them more willing to make changes. If a change is very costly, customers don't do it often. You see this a lot with customers where they don't want to do big changes like image upgrades because they're used to doing it manually. They take a lot of time, they're fragile. When we can make changes more repeatable, smaller, and faster, customers are more willing to do them. Here we also have an example of what it looks like if you were to do the same workflow without CVP. In this case, the big thing that changes here is that Ansible becomes both your orchestration and your provisioning engine. It's pulling data in, it's building your templates, but then on top of all that, like it was before, it's now reaching out directly via API to all your devices to then push the config changes and do your validation. This is an option some customers do. It creates more work for them because they can't take advantage of built-in checks and tests that we have in CDP. For example, things like rollback commit, they might have to do themselves via play changes or tasks. But for customers who want to go as open source as possible, you might see something like this in place. So what we've just gone through is the basic philosophy and reasoning of why we would want to automate and a vision of how we might do that. Now we're going to start getting to some terminology and concepts. We're going to start with API specifics. And then once we go through some different API examples, we're going to start getting into Jinja as well. So pretty much everyone here has already gone through Python. We aren't really going to cover that with that being a prereq, but APIs are something we're going to focus on pretty heavily in this because they're key to how we talk about interactions between code you write locally or on a server and the rest of products. Very simply, when we talk about APIs, that just stands for an application programming interface. It is a definition of how your code can interact with the product. There are products out there in many domains that don't have APIs. And that doesn't mean you can't interact with them. It does mean it becomes more brittle. As an example, for a very long time in the networking world, you really couldn't get an API to networking devices. So a lot of networking scripts would do essentially screen scraping over SSH. You would have your code open up an SSH socket to your device. It would get a CLI. And you'd have to tell your script basically, when you see this pattern, it's a new line. When you see this pattern, you're in enable mode. If you see this pattern, you've been disconnected. And you would have to basically teach your script how to understand whatever arbitrary input you go back and switch. This gets brittle for a lot of reasons. And so historically, automation in the networking world was a little more brittle, not fun to do. With APIs now available on networking products, and there's a lot of different kinds of APIs available depending on your vendor, it becomes a lot easier to think about doing this. You have a more well-defined expectation of what you'll get from your device, what you can send it. It's clear to delineate when a command is ended, when your output is finished sending to you. And all this combined to make it much more easy to reason about what you're talking to back and forth with your devices and how you can change them. When we start talking about different kinds of APIs, there's two we're going to focus on today. That's REST APIs and JSON RPC APIs. REST stands for representational state transfer, and it's been the de facto standard for a very, very long time in how people interact with HTTP-based APIs. It's a very verbose way to write an API. Effectively, for every object you might act upon, you have a set of verbs and paths you would use for that. The benefit of REST APIs are that they're very easy to understand. They require minimal tooling to work with, and they allow you to explore them without any kind of extra documentation. They're often defined as self-describing. When we talk about JSON and RPC APIs, you're really bringing in more technology to make the overall communication more concise. For one, you start sending data to your API endpoints with JSON. And for those who haven't seen it before, it's the JavaScript object notation. It's also its own data format. It's very similar to what you can get if you pickle a data structure in Python, but there's some differences in nomenclature. RPC is the more interesting part of this. RPCs are an old concept that become new again. They stand for remote procedure call. Effectively, with an RPC, your code is calling a function that is not part of your code base and does not live on your device. So whereas in a normal script, you might call a function you have like get route table, where you have it locally. If I'm doing it with RPC, what happens is I'm not having my code make a call over my API within my actual code environment. It's calling out over some format in this case JSON, over a network to a remote device, that device runs the function on its side and returns the results to me. For a number of reasons, this is more compact, but it also requires more knowledge of what the procedure call can accept and what it returns. So whereas REST APIs are self-describing, JSON RPC calls usually require some knowledge beforehand of what the schema will look like. There's also a third type API call here we really won't get into as much, but you will see in our docs, and that is gRPC APIs. A gRPC API is similar to a JSON RPC call in that it's a remote function calling on the remote device, but they use something called a protobuf, which encodes things to make them very small and compact across the network, but they are not human readable by default. Finally, when we talk about YAML and Jinja, YAML is a recursive acronym in Grand Old Linux tradition, and it just stands for YAML ain't markup language. It is another way of describing data and laying out data in files. And then Jinja is one of the main Python templating libraries you'll see out there. It is the one we use in Ansible, and it's the one we'll be using in our labs for Python as well. Alternatives to the Jinja are pylons and Mako are some common ones. We do support Mako as well as Jinja in CloudVision, but the other ones aren't used as much. So APIs. We talked about the brief definition, but what does it actually look like in practice? Well, when you start communicating with devices over APIs, we start breaking up into these discrete request response cycles. I'm not trying to now scrape a synchronous socket like I might have been in the old days of SSH to a device. I fire off a well-defined request of some sort, could be an HTTP post, could be a push across my socket for gRPC, and then it arrives at the API endpoint. The device does some work on the back end and gives me a response back. If you want to put that in human terms, it looks something like this. You're at a restaurant, you want to place an order and get a pizza, you look at your menu. You tell the waiter, I want a 16-inch sausage pizza. He takes it to the kitchen does work. You don't have to know the details how they're making the pizza. All you know is that I get a pizza back. On the back end, this could be they have to form a dough, add the sauce, add the cheese. That's all abstracted away from what you're seeing by your API layer, the waiter here. So when we start talking about REST APIs, specific to their style is that, like we mentioned, it's that self-describing architecture. And you'll see some argument between people typically about how RESTy an API is or isn't. There's various levels of definition that people have for them. But overall, what you're going to see with them is that it's going to be an HTTP API, and you're going to send some data either as HTML, JSON, XML, and you're going to get back your response in those same formats. And typically, when you look at these APIs, either to explore them or in their definitions with something like Swagger, which we'll look at as well, you'll see that they're using different HTTP verbs to differentiate between operations as well. Get, post, put, and delete are the most common HTTP verbs you'll see used in their APIs. They can include other verbs as well, such as header options to do different changes with their API endpoints. When we talk about how RESTy something is, this is what we start getting into. In general, REST rules state that when someone is designing a REST API, the verb should describe the operation, not the endpoint. So if we want to delete a user, REST rules would call for hitting the API user's ID endpoint with a delete verb, and the server interprets that and does the action. Something not RESTy would be if you say, hey, hit the delete endpoint for users with that UI, with that user ID with a get call. You will see some APIs like this out there. They are not considered very RESTy because they break convention and assumptions around how your API layout should go. Like you saw in the previous slide as well, when you're dealing with REST APIs, the scope of what you're affecting with the API call is put in the actual URI. And this is going to differ from JSON RPC rules, which I'll show you in a second. But effectively, when we're doing operations that are scoped to part of our domain, in this case, a user who's part of a user list, it's the entire thing, we put that scope information somewhere in the URI. It doesn't always go at the end. That can depend on some API conventions, but you will see it built in this way. So let's talk about one of the main REST APIs you're going to see with the rest of products. This is the CloudVision REST API. CloudVision does have a number of different APIs it does use. We have REST APIs, we have gRPC APIs, but this here is our main set. A long time ago, we were not REST compliant with the API. This is back in the 2018 days. So you'll see here, we would do things like make a post request to delete device inventory. Things like that break conventions and cause some confusion sometimes. So these days, and this is even old these days now, we do have REST verb compliance. And like you can see here, and like you'll see in the lab later today, we have a number of different endpoints available within CloudVision to do operations. And it's common when you're looking at documentation like this in tools like Swagger, that those tools for the documentation will color code the endpoints by what the verb is. So you'll commonly see get calls in blue, post in green, deletes in red. And that makes it visually apparent as well when you're looking through API documentation about what a given endpoint and verb combination will do. So what does it actually look like in practice when we make an API call? This is a curl example here. We'll be showing some of these in labs as well using the request module with Python. But in general, when we start taking what we saw on this slide and transforming it into a call, what we're doing is we'll set our verb. We'll tell the endpoint for the API, yes, I accept responses in a JSON format. And then we'll give it our URI to hit. And then once you hit that, assuming you are authenticated, able to talk to the system, you get back a response like this. This is a very large, well, this is a JSON blob that shows you all the different devices you have in your inventory at that time, as well as data about them. From here, you can then take this information and parse it with code or whatever database solution you have to then perform further actions on this. Within CloudVision itself, if you want to see that Swagger documentation we talked about and view that or play with the individual calls, we have a tool within CloudVision itself called the API REST Explorer. Like this is showing here, if you go to the gear in the top right of your CloudVision instance, and then after doing that, you click on REST API Explorer here, circled in red in the sidebar. This will bring up our complete REST API documentation along with a Swagger tool to let you explore with this. Now, you may have heard me say Swagger a few times by this point. Swagger is OpenAPI v2. It was originally called Swagger, later given a politer name as OpenAPI v2. Now they're an OpenAPI v3. And what this is basically a way that you can write REST API documentation in a common format that a number of open source tools can understand to do things like render documentation, like this is doing here, create calls against it automatically for exploration and faster code scaffolding, or you can validate it with different tools as well for things like health checks and uptime visibility. When you look at any individual REST API call in the REST API Explorer within CloudVision with a Swagger view, you'll see it's laid out like this. When you click into any of those calls it expands. We give you some documentation about how this call is supposed to work, any caveats that might happen if you don't provide certain parameters, and then we give you a way to try it out. For this call here that we're showing, this is just a get call on inventory containers. It will dump all containers to you. If you want to filter what it returns to you as a user, you can also give it a query string that will then filter down what it shows you. Hitting try it out here enables these views and lets you actually play around with it. And then below this, you see responses and the actual response of your API call. So let's get into JSON. We talked about this one before. This is the JavaScript style of data structures, very similar to Python style in that we have lists, maps, all of your classics. It is also its own data interchange format, whereas something like pickle serializing is specific to Python. JSON can be written to disk and run a number of tools. It can be transferred between languages. Most languages have library bindings to translate JSON into their internal formats, and it's human readable. This has made it a really good tool when doing web work with both APIs and websites, device APIs, things of that sort. So you'll see it very commonly used. Nomenclature is fairly simple. You're going to see that it looks similar in a lot of cases to your Python format for lists and dictionaries. Some small differences in how you'll see it done on disk sometimes, but in general, your JSON object is going to be like a Python dictionary, and that has curly brackets to wrap it, and you have key value pairs, commas separate them. When you look at a larger example, for example, if you run any of our commands through our JSON tool on box, you'll see it emitted like this. This is one single JSON object, again, Python dictionary. And within that, we have a number of different keys and values. Values here can be things like floats, they can be strings, they can be numbers, or they can be Booleans. All those are valid within JSON. So with what we talked about there with JSON, we can now start digging into how a JSON RPC works. Like we said before, the JSON RPC is considered fairly lightweight in the RPC world. It doesn't require you to have predefined schema on your actual code base for what you're sending. You write a JSON object, you send it across the wire, your remote side reads it, operates on it, and sends a response. Something like protobufs you'll see with gRPC, you actually have to have a language native schema and class typically laid out to handle the request response cycle across your network call. The main thing you're going to see as well when we start talking about JSON RPC APIs and using them in the labs is that unlike a REST API, which might have tens or hundreds of thousands of endpoints to do different operations, a JSON RPC API typically will have one or a few endpoints. Case in point with eAPI, our API on the rest of EOS devices, we have one endpoint you send calls to. What matters is the payload. The payload you send to that endpoint is everything, in contrast to a REST API call. So, for those who haven't seen this before, this is the Command API Explorer. This is a web page you can get on any of our devices if it's on. And what this does is this gives you a graphical way in your browser to run commands against the device and also see the request response cycle we're doing with JSON RPCs to accomplish that. So in this example here, all I'm doing is I am doing a show version on one of our lab dots with this, and then we fire it off. What we get back then is this structure in JSON format about the results of my API call. couple things you're going to see here. One, we now have nested keys because we have a multi-layer dictionary in Python parlance, objects in JSON. And I also have this structure I have to reason about internally. JSON RPC defines a few default keys that are always there, but then the main key you're looking at when you're working with eAPI is your results or error objects. And what those are going to have is the actual outputs of the commands you've run or any breakage you've experienced. If we have errors, like in this case, I haven't run the fully worded out version of show management API HTTP commands, my response changes dramatically. You'll see now I have this error key in my top level object, and inside that, I have data for each command I run in sequence. The first command I ran, show version, was fine, so it returns the data you saw in the previous step. But then for the next object, where my command was incomplete, it gives me, instead of a response, an error object saying you didn't have a complete command there. So it's structure like this that you have to know more about and reason about when you start getting into how to use a JSON RPC API. Luckily, we have ways to help with this. When you look again at that Command API Explorer in our box, we also list the schema used to both send a request and get a response. The endpoint is always the same. It's always the same URI to talk to our box. What changes is going to be your method and your params. As of today, the only function that we have on our API is run commands, because that can do everything. That can do configuration, that can do show. So it's all under this top level RPC called run commands. Within that, your params dictionary is actually what you are passing to this function when it runs on the remote side. Think of it like what you would pass as your arguments to fast CLI when you run fast CLI in Bash. Within here, you can see my commands key of my params are set to run this list of commands in that schema example. We also have schema examples of what success and failure look like. As you can see here, for a success case, you'll have your results with any outputs if there are. If a command does not return output, for example, something like enable config T, you just get a blank. If you have warnings from a result, you'll see this here. And show commands then give you their own structure. Show commands will give you the same schema you would see if you ran that command through the JSON pipe filter. So if you're trying to plan for an advance, that's only you can find out the schema. Or what you can do is get the response and programmatically step through it for the keys you're interested in. When we talk about failure, again, like you saw before, you have, instead of results, you now have an error key. And within that, we can give you things like data on a per command basis, what failed. We can give you an overall message about what went wrong and an error code. And these may or may not be useful to you, depending on what your exact use case is. And from here, if you were failing, you either want to be able to handle it in your code base, or if it was a schema issue, iterate upon that to then get your desired result. Does anyone have any questions on the API schema before I jump into YAML? Okay. So, like I mentioned before, YAML is a markup language that tries to claim it's not. It also got a Genie recursive acronym, which is basically running inside GAG of acronyms that are themselves their own acronym in GNU and Linux projects. It's a data serialization language that's similar to JSON, but it's not quite the same. It's used in a number of languages as well. It can be interchanged in pretty much every language that JSON can. and it is the main way that Ansible will store and look up data. When we look at this, it can be a little tricky to look at sometimes if you are not used to seeing white space indented data. Unlike JSON, we do not use brackets and curly braces to denote objects. It's all white space hierarchical. If you need to validate if your YAML is good or not, quick way to do that is the YAML lint tool. And if you need to look at how the actual language specifies different kinds of objects, YAML.org. Data structure of YAML is going to be different than things you have seen previously if you haven't been exposed to it. Every YAML file, you start with 3 hyphens, or it can be implicit, depending on parser. You always indent when you have a subkey by 2 spaces. You don't use tabs here. If you use tabs, you will break it and terrible things will happen to your code. Like JSON, like Python internals, we support lists, dicts, integers, strings, all the various good stuff. What you'll see though is that when we look at the actual formatting techniques for a given dictionary, in this case, we've got a top-level dictionary where key is 493, value is an internal dictionary with more keys. It's all indented. So in a heavily nested YAML file, you'll start seeing indentation go all over the place. And typically, if you're using some kind of IDE, it can help to put on extensions that color lines based on how deeply indented they are. So looking more at how YAML will write different operations in our languages, in both JSON and Python, your list is going to be square brackets, object 1, comma, object 2, comma, object 3. In YAML, you get something that looks like this, where within your list object, you have 1 item per line, start with a hyphen, and it's indented. Key value pairs do not have curly braces. They do not do commas. It's based on having a colon between your key and value, and then new line to next item. And then dictionaries and maps are basically indenting rule on these 2 concepts. Like in other languages, dictionary keys are not guaranteed to be ordered. If you need your dictionary keys to always be in a certain order, you have to handle it yourself. Your lists are ordered, and then your Boolean values are true and false here, lowercase, not uppercase like in Python. So let's take what we just talked about with YAML and look at what an example of an Ansible playbook looks like. Every Ansible playbook is itself a YAML file. So here we have 3 lines, start a file. And then what you'll see here is that we have, in this case, a top-level list with 1 item, which is a dictionary. Dictionary has a number of keys. And then for a few keys, we have sub-objects. The collections key has a list embedded within it. And the task key then has another dictionary embedded within that. And import role has yet more embedding. So like we mentioned, what you'll start to see is that as we go down the nesting hierarchy, we're indented further and further to the right, which is your visual indicator of what it belongs to. And this is also why, if you're not sure about the spacing or layout of a file, a tool like YAML lint is very helpful, because that allows you to understand if you missed a number of spaces somewhere, if your indentation wasn't expected, so on and so forth.
Is the number of spaces a matter, or is it just like any number of spaces?
No, yeah, it does matter. It's always 2.
Yeah, sounds good.
Yep. So that's a good point. Yeah, if you wanted to, like, in this case here, this is double nested. There's 4 spaces here from this key, and then hyphen and space. So you will start seeing a significant amount of spacing. And that's also why tools that color your indentation are very helpful. I use one called, I believe it's Rainbow Indents in PyCharm, what that does is every indentation level gets a different color, which gives you a very, very good visual indicator of what your indentation is in case you fat finger your spacing. So,
But like spacing doesn't really matter. Like the indent doesn't really matter as long as you just have at least one space.
yeah, if it's the same, it'll catch on to it. That's usually a parser independent piece of logic. The standard calls for 2, but most parsers these days, like Mas pointed out, they've learned to account for usually between 1 and 4. Some do any amount as long as it's the same number.
Yeah, and
But
in some places you will see that, for instance, if you have a list, then they don't even indent it. They put the dash under the parent. Like if you look at CVP Kubernetes manifests, all of the lists are like that.
yeah,
So
and
it can be
technically
a
that
bit
does break.
confusing.
Yeah, that technically breaks the YAML standard. But again, most libraries these days have learned to handle somewhat bad inputs, and so they can account for that. But if you're writing quote unquote proper YAML, it's always 2. And then here, this is just a quick example of what the same data structure might look like in different languages. So for those who've ever had the disappointment of writing XML, this is what your data structure might look like, where you have nested tags, definition internally, and then overall tags. In JSON, we can strip away a lot of that boilerplate tagging. We just have our overall hierarchy. We've got dictionary, key, list. Dictionaries is another list. In YAML, it looks nearly the same. The big thing you see is that we've swapped out our curly brackets and our commas for white space rules. So here we aren't caring about brackets or commas. We're caring about new lines and indentation. So now I get to the fun stuff. Jinja 2. Jinja 2 is a templating engine. What that means in easier to understand terms is that it's a bunch of format strings on steroids. You give it a overall skeleton of something you want to write. That could be a cube YAML spec. It could be text. It could be an email. Anything that you can give a skeleton for. And then you plug in variables into your templates to say, replace this chunk with this text, or the contents of this variable, or if this variable has this value, do this thing. That's what the templating engine is. Jinja is special in that it was written as part of the Flask project originally for Python. And what it does, much like the Flask project came from, it really tries to reuse every concept it can in Python before adding its own. There's very little additional magic or convention you have to learn with Jinja. And when you do, their documentation is essentially 1 page long, but it gives you a very nice and easy way to do a lot of text composition in a fast way that you can easily understand. As you get to larger and larger compositions, like an entire switch config file, just using format strings in Python in a loop begins to break down. It becomes hard to reason about when you're trying to interlace your business logic about the actual contents of your text with your control logic of your loop iteration, variables, things like that. When we use Jinja, we can separate those two concerns, and it allows us to create much nicer blocks of template code to look at. And then we just shotgun variables into it once we've done our initial setup in Python. So, like we mentioned, Jinja is pretty easy in terms of syntax. The big things is that when you give it a template file, by convention, it's going to be a file.j2, and you'll see this in the lab. You'll build your own, and we'll have some examples as well. It's basically a text file, and we load it into Python for interpreting by the template engine. Within those files, anytime we're using a variable, it gets put within double curly brackets. And then our control expressions for loops, if statements, those sorts of things. Use single curly brackets with percentage signs. You can also use expressions to do things like pick the next available IP address using some Ansible magic. You can use them to lowercase, uppercase variables, things like that. And of course, you can always write your own filter syntax for expressions as well in Jinja. You need to extend it. Looking at this here, this is a very small example of a template you might end up writing in Jinja. In this case here, what's happening is I've got text of just load interval default, and then I'm going to have the Jinja template engine when I run the template take the value of my load interval variable, the default key internally, and it's going to take that value and drop into my template. And this entire part of template is only expressed as text in the final result if load interval is defined and it's not none. So in my overall template, if I didn't have this variable defined, or if it was none, then I would just skip this. I wouldn't emit that in my final config. If statements, like you saw on the previous slide, allow you to do more logic and make templates with branching outcomes. So you can start doing things in your templates like, say, if this is my first MTP server, give it the preferred keyword. If I don't have AAA, skip that. If I have AAA and I don't have a user, configure one, things of that sort. If statements overall are very lightweight in Jinja. They are different than you see in Python just because of how they work with text logic. They always start with this curly bracket %if statement here you see in green. And this is going to be your test to see if you go into this block of the template or not. So in this case here, if my AAA variable was defined and it was not none, I go into this block. There's a further if test in there where I see if now I know my AAA authorization variable is defined, is the exec default key within it defined? If so, I then emit this. If not, for this overall AAA block, I would do no AAA root. If this overall green test failed in Jinja, I would just emit no AAA root. The big thing you're seeing here with both orange and green, unlike Python, is that you can't just do your if test, indent some code, and return. You have to explicitly close the end if. It's going to be the same with for loops. And the reason for that is that because we're doing multi-line outputs like this in Jinja, and the text indentation is independent of code flow, we can't just use indentation to reason about if the if loop has been closed or not. We have to explicitly tell our templating engine, I've now closed my if statement within this template. For loops, similar concept. Again, we have a control block, curly bracket, %sign, and then we have our for keyword, and we can actually get into our loop iteration here. One thing you're going to see a lot in Jinja is that when you call a Jinja render, you give it a whole bunch of arguments you want from your Python environment, and you define all of them, and it loads them into what's called a template context. At that point, then, those are available for you to use within your templates. So in this case, this is an example. I've called my Python Jinja render with my Python code, and I passed it this VRF's object. So now I can loop over this using standard Python syntax for VRF and VRFs. So it iterates over it one at a time. We go through, and I'm then going to emit IP routing VRF, value the VRF variable at that time, and for, and if. Filters. Like we talked about these are transformations. These occur within Jinja before it emits it to a template. There is a number of built-in ones, and you can write your own. Ansible also has filters in place for doing things like picking a valid IP range within a given pool, assigning a next IP, escaping sensitive values, things like that. Effectively, what happens when you have a filter is Jinja will go it will evaluate your variable as you usually would. So in this case, we'll pull the value of description, and then we pass it to a function called upper. There's some backend magic here with Python, which you can look at if you want, about how built-in filters work and how you write them in Jinja. But effectively, we pass this value to this function, we get a response back, and that is then the final value we put in the template. So if I had like a lowercase test here as my value description, like it's passed to this, we make it uppercase. My final template output is going to be description uppercase test. So we're going to run through a very basic Git primer here as well to get everyone ready for the labs. One of the things that we do in these labs is we do provide answer keys as a separate Git branch. And we're also going to be talking about some of the other applications of Git as well for networking when doing networks as code. This is not going to cover all of the different Git operations. That is a much longer topic than we have time for. We are going to cover the basics of doing adds, commits, checkouts, and the like. So when we talk about Git, Git is a code storage system. For those of you who've never worked with those before, this is basically a way that you keep copies of your code at various points in time for use by you or others. There's a number of reasons you would use something like this. One is obviously backups. You don't want to keep all of your code just in your system. If you lose your laptop, it all goes away. That's a big problem. The other would be collaboration. It's very hard for everyone to work on code that's just in your laptop, unless they all feel like emailing you files or sending you links over Google Hangouts. It doesn't scale well. By using Git repositories with remote repository logic, we can all work in the same code base and make changes, and it's much easier to actually collaborate. The other big reason why you'll see people use this is so that you can look at how the code has changed over time. And this can occur both in a time-based view or in a branch-based view, depending on what your Git workflow looks like. An example, this would be something where I have an Ansible playbook on my network that goes through and deploys a certain ACL. Now, Thursday comes around, my boss says, hey, can you update the ACL to include Google today for some reason? I go, okay, sure. I make them change my playbook. I roll it out. Oops, turns out people needed Google. In the older, more manual networking world, where you don't have things like Ansible or Git laying around, if you didn't know the exact change you had made that caused the issue, it becomes very hard to back that out. Obviously, changing one line in ACL is a simplified example. You can imagine much more intricate changes. When you get to that kind of state, if you have something like Git in place and you're tracking your changes for Git, it's very simple to fix that. All I have to do is do a Git checkout on my last known good revision that pulls my file state into my actual directory I'm looking at. I run my Ansible playbook again, it backs up the change, network is good. That's the vision a lot of customers want to get to. Not just how quickly they can roll out a change, but how quickly they can roll back a change. So Git is a critical part of that. When we talk about Git itself, there's a number of different places within the code logically you have to talk about. The workspace is where all your files live when Git is looking at by default. This is before you have a tracked copy of them or your changes are staged in the index. This is what you would see if you looked at the actual file system. As you go through and you get files ready for getting bundled into a commit to be stored in your Git repository locally, you'll usually add them to your index. This is a staging ground where you'll basically get your changes ready, make sure they're all ready to go for that set. It makes sense. This part can differ from person to person, depending on workflow. From there, once you have a set of file changes ready to go that presents something to you, you would commit them to your local repository. So examples could be something like you create your Ansible group vars, your configuration, your inventory, and a playbook for a given task, like pushing this act we're talking about. You would get them ready in your workspace. You would add them to the index. You would create one commit in your repository saying initial commit, inventory, and playbook ready to go. All well and good. Then, as you make changes to the files in your workspace, you would then repeat moving the changes to your index and putting commits in your repository, and this builds your Git history. You can, of course, bypass the index if you feel like living dangerously and just tell Git, take all my changes to my files, my local workspace, and dump them into a repository. That's also available. It's done less often, but it is a valid workflow, depending on your Git workflow looks like. You're going to hear me saying a lot because Git is a very flexible tool made to do a lot of different workflows. At this point, we then have files in our local repository, our green copy, that's still only on our local computer. If we want to share our file with someone else, the main thing we're going to do is we're going to put them in a remote repo they can pull from. So that's going to be something like GitHub, GitLab, or your Git server of choice. It doesn't have to be a hosted product. It's effectively a repo that's open over the network that you have access rights to push to. So when I'm ready to share the changes I've made to the repository history with everyone else, I push, and what happens there is my Git client calls up remote repository. It compares my commit log and my commit history between local and remote, and then it will ship the delta of commits from local to remote along my notes. And then they will live there. At that point, then, anyone else I'm working with, or even myself on different computers, I can pull that down to my local workspace on those computers. So if, let's say you're working across like 2 laptops and a desktop, you might write code on one of them, you'll commit and push it up to your GitHub server, then you pull it back on the other 2, work on it there, also valid. If I was working with someone and I wanted to see what changes they've made, but not apply them to when I'm looking at my files, I can just fetch their commits. They'll pull them down in my local repository. I can look at them. It doesn't actually affect the files I see on disk. When you check out or do a pull, that does pull those remote changes down in the remote repository into your local workspace. And then, of course, like everything else in the world, we can diff those files against both the index and the repository commit to see what would change if we applied these operations in our local workspace. Most of Git's workflow is based off of chaining together simple commands like this into more complex operations. It can seem confusing at first, but overall it's fairly simple. We will have a few different Git operations in the labs to walk you through some of this and get you familiar with how you use a Git repo in daily operations if you don't have familiarity with that. So like we talked about, just rehashing this here, when we have Git changes that go through, we have working directory, we have index, we have repository. You'll typically flow your changes and files from working into your index for staging. Once your index state is ready, you'll commit it as a batch to your repository. If you wanted to back out a change you'd made from staging for your commit, you weren't ready to push it yet, had a dependencies or something, you can unstage your index back to local only. So let's say you're actually in Git now, or you're on the command line, you want to use Git, you want to see what the state of your setup is. You've just initialized a folder where you're holding files for your labs as a Git repository, and you run git status. What git status does is it shows you the state of all the files in the directory, the files in your repo, and any differences. In this case here, what it's telling you is that, okay, repository is currently on branch master. You don't have any commits in the repository yet. And I see a whole bunch of files in this directory that you are not tracking. And they'll tell you, if you want to add these to Git to track copies of them, use git add. So at that point here, we have 3 files with changes. Changes here being that they don't exist in Git yet. And there's nothing in the index, nothing in our repository. At that point, we want to add those files from working directory to the index so we can commit them and save them. So for that, we run git add. There's different ways you can run git add here. You can do git add and then glob pattern to pull in a whole directory or a path. You can add individual files, or you can add everything. Once you have them added, if you run git status again, at that point, then you'll see new output. You still don't make commits, but you'll see you have changes to be committed. It'll tell you leaf.j2 is now in the index. If you want to unstage it, run this command. And these two files are still not part of the index and still aren't being tracked. So, like we said, you can use glob patterns here. Git add dot, just that's all files in current directory, to your index. If you then run git status, you'll see we have these 3 files here that if you run a commit, we'll add them to the repository. So at that point here, you know your files in your index. Like we showed on the previous output, where it said you can unstage an index. If we decide that the leaf.j2 file, our template for leaf2, was not ready for staging to a commit, we could reset it like this. And then you run git status, you'll see that we are now no longer holding leaf.j2 in the index for staging as a commit, and it's not tracked. At that point, your state would look like this. You have changes to leaf.j2 in working directory only. You have your changes to leaf.json and main.py in the index. And now we decide, okay, J2 is ready. We add it again to the index. We want to actually make the commit, get our code stored. At that point, we would run through and we would use the git commit commands. What you're seeing here with this -m option is this is the commit message. If you don't do -m with a string to git commit, it will open up an editor where you type in your commit message. This can be 1 line or it can be as many lines as you need. And then when you save that, it writes the commit to the repository. Commit messages are important. It's one of the main ways you'll be able to find things in history later when you are looking for changes months or years later. So messages like first commit, second commit, third commit are not very helpful. Whereas messages like altering the leaf template to account for changes in underlay restrictions gives you something much more helpful for a search on later if you have to look through a lot of commits. There's tools you can use that, given a fragment of a commit message, can tell you what commits that appeared in, and then you can look at those to see what the changes were. There's also tools like git bisect, which we won't get into here today, but they give you a binary recursive search on your Git history to find where a certain change happened. With the commit done, if you're in git status now, what you'll see is that we're still in branch master. We now have commits, which is why it doesn't say no commits yet, and it also is working tree clean, meaning the code we've committed in Git is matching the files on disk currently. There's no difference between them. At this point then, our changes are safely stored in the repository as a commit set. So then we decide that we need to go and edit leaf.json. We've got new IP ranges. Maybe we're changing a banner or something. In this case here, we're adding a VLAN. So we change line 18. After that, run git status. Git can pick up that you have made changes to the file. It will tell you you've changes. They are not staged for commit yet. And it will always try and hint to you different commands you can run to do different operations. At that point here, with the change to leaf.json, we have it in working directory. We don't have our changes to this file yet in the repository's new commit set. If you run git diff here, what will then happen is we will show you the output that is different between your on disk copy and what's in the repository currently. So here you can see the previous file. When we look at that line in Git, it had VLAN 1030. Now, when we look at it, it has you on 10, 30, 40. With that, as long as we are ready to add that change to repository, we like what the change has been, we know it's done, we add it. And at that point, if you run git diff, you would see nothing because your change is now in the index, not in working directory. Then you commit that, Git runs this commit operation, tells you, okay, this commit changed one file, one insertion, one delete. And that's how we basically work with Git. We just stack changes and commits on top of each other into this tree hierarchy, and that gives us our history to work through. If you did need at some point to look at the difference between a file in the index and repository, that is also possible. What happens with that is that you're going to use this cached option, and that changes what Git looks to the diff. So in this case here, if we had leaf JSON, and we had it in working, and then we added it to index for staging, if we still want to diff our change here against what's currently in the repository, we would use the cache flag. I've been talking about how we have this tree of commits and how that works. This is really where it comes into play. Git has a concept of branches and ancestors when we talk about commits. So you'll see this done as well with EOS. The way we do release trains is effectively we keep branching to do a given numbered release. And when you start looking at this at first, it may seem confusing. There's different ways you can make it easier, graphical tools, color coding, things of that sort. But there's no exact main line in a Git repository by default. Many repositories will say we are using a master branch, we're using a main branch for our dev work or something like that to make it easy for them to work on by convention, but it's not part of the actual Git protocol. In addition to that, you can then have branches that come off with any other branch, and they can exist temporarily or they can exist forever. You can also have branches of branches, because all Git is looking at is your ancestors of a commit. So what this can look in practice is, I go through, I'm a network engineer customer, and I deploy my initial files for my Ansible set for our fabric. I've got our config, I've got our inventory, I have our playbook. I commit that. Then my coworker Bob comes along, and he starts working on adding our ACL definitions to our playbook. So he does a few commits in his branch, he does some testing. Once that ACL feature work is done, he merges it back to mainline, our master branch. At that point, if someone had checked out master, they would then see, okay, I've got Bob's ACL work and I've got the initial work. While Bob's doing that, we could also have another engineer, let's just call him Hank over here, working on our BGP specs or something. He can do that work at the same time, merge it back in. So this is where you'll start to see a lot of this history come into play. And like mentioned, the reason that you would see branches used is for something like a long-lived maintenance release. If you ever look at the Arista repos and you look at how we do a given release, once we get to a maintenance mode, you're basically seeing people put commits and tags on a given branch. That branch exists until we drop support and prune that software release. So with that shock information we've given you, now we're going to start getting into the actual lab time. For pretty much all of you, you should have gotten an AVD topology already. If you don't have a link for me, let me know, and I can get you a topology link for your AVD instance. I've turned on all of your instances so far. You should be able to get into all your AVD topologies and then get into the both CloudVision and VS Code tabs within that. If you can't, let me know, we'll figure it out. And we then have 4 labs that we're going to go through today. For all these labs, we've provided an answer key. If you need it, you can get it via Git checkout. Doing git checkout in this format of answers dash lab number you're looking for will pull those files in your local directory so you can see an example answer of how to solve the lab. After that, if you want to check back into your code, doing git checkout main will put you back on your main branch. You, of course, are also free to do your own branching if you want, tags, anything else you feel like. So, labs for today. We have about 2 hours for this. First lab is going to be just a quick example and walkthrough of how we would use the API with Python and JSON RPC formats. So for this, you'll be using the request library in Python, and you'll be crafting a JSON payload to send to the API endpoint for a JSON RPC call. So you get some information back, and then you'll just print it out nicely in Python. So that'll walk through crafting JSON, using the API, getting it back, and post-processing it. Lab 2, we're then going to get into using Jinja. We're going to, again, talk to the API, get the output of various commands, and then we're going to use a Jinja template it'll create to pretty print information and give you some summary views of the MAC and ARP tables. For lab 3, we are then going to start looking at the CUP REST API. For this part here, you're going to take a look at actually using the API Explorer in CUP to find various methods that you need. And once you have that, you'll then again use the request API to hit the REST API endpoints for CloudVision, get the information back, and print it. You will need something called a bearer token as well. Instructions on how to get this are in the lab instructions in the lab files. And if you need help, of course, just ask me. Lab 4 should be simple. This is just basically a Git and GitHub primer. If you don't already use that, you'll just make sure you have a GitHub account and you have a SSH key for it installed from your AVD instance so that you can save your lab work here to look at later if you want to. And then with that, let me put in the chat here the labs for today, and we can get started on those. I'm gonna stop sharing my screen. We'll stay on the call and we'll stop the recording, and people can start getting into various lab work. This link in chat here is our GitHub link. You can clone this directly into your AVD instance, and with that, you'll have 4 folders there. They each have a README for the lab instructions and example files as needed. For each given lab, you'll either have to alter the example or write your own to achieve the output that the READMEs are looking for. When you're doing the git clone, just make sure you clone it into day 1. I know some people tried using the VS Code clone button and it just kind of dropped it in their basic directory. That's fine, but if it does come with some lab files already in place, that might conflict. I believe there's already a lab 4 in place there. So just cloning it into your day 1 folder will avoid that. Any questions for me so far on that?